name is Patton, and I'm a geologist at Humboldt State University. And so I've come here to tell you a little bit about the earthquake, tsunami, and sea level rise hazards associated with the Cascadia subduction zone here in Humboldt County. So let's go ahead and get started.
Yesterday's earthquake.
Oh, well, maybe we'll talk about that too. So I have a couple slides at the end, and maybe this needs to turn on, and we will just use the keyboard instead. Okay, so here's a map of the subduction zone, and I'll tell you a little bit more about it, the title of my talk, and of course I want to give credit to all the people who have done the work on the subduction zone that I collaborate with, and I would like to give them credit. I will be posting this PowerPoint, this visual presentation, will be posted online on my website at earthj.com. And you can email me, and I have business cards if you want to get a hold of that exact website. And I'm videotaping this, and I'll put the video online also.
Cool.
All right, so first of all, just to keep you guys all awake, I want to get you guys to do a little exercise with me. So we're going to put our fingers on our wrist, and the fingers are going to be stuck on the wrist, and that's the earthquake fault. And then I'm going to show you what I want you to do so we can do it together. And what we'll do is keep our arms relatively horizontal like this, and we're going to move our elbows together and let our fingers and wrists flex. All right, so when I move my elbows together, which is the plates converging, see how my wrist is going up and my fingers are going down? Now, what do you think is going to happen when that fault slips? What's going to happen to my fingers? Yeah, the fingers are going to go up and the wrist is going to go down. And so here we have the earthquake cycle. Fingers are going down. In between the earthquake, the wrist goes up. During the earthquake, the fingers go up and the wrist goes down. So we'll think about that throughout the talk. So I'll be asking you, are we in the finger part or the wrist part of the subduction zone?
Are there tests at the end?
There are no tests at the end. So no grades either. All right. So this is a little diagram from Brian Atwater that shows this same earthquake cycle. Here we have the interseismic part of the earthquake cycle in between earthquakes. You can see here that the plate is locked. This is where the fingers are, and it's being dragged down. And then this part of the crust bulges up, and that's the wrist part of the subduction zone. And then, like you already know, when the fault slips, the part that was going down, the fingers go up, and the wrist goes down. So that's the earthquake cycle. I'm going to be visiting that. Excuse me. So here's a photo that my colleague Kenji Satake took following the 2011 Tohoku Oki earthquake. And here along the coast of Japan, these areas are all rice paddies that generally were above sea level before the earthquake. And now you can see that they're flooded. And so what part of the subduction zone are we? The fingers, the wrist? The wrist, that's right. So it went down during the earthquake, it subsided, and now we have flooded land. And I really like this because it reminds me of Humboldt Bay and the Eel River. So here you can see this might be Arcata Bay, South Bay, in the Eel River Valley. So it might be something like what we might experience here during the Cascadia subduction zone earthquake. Now I'd like you to take a look. Here's a little model that my colleagues from Caltech put together, just another visualization. And look at the island with the palm tree on it. And as the plate is locked and this island is subsiding, the fault slips and it goes up. So it's just another visualization. And on the left we have our map of the Cascadia subduction zone, where I found the on switch, where the Juan Fuca and the Gorda plates, and also the Explorer plate, subduct northeastward beneath the North America plate. And so here is the cross section, A to A prime, A to A prime, and you can see that here we have the Gorda plate is subducting beneath the North America plate. And this shows the interseismic part of the cycle and the coseismic part of the earthquake cycle. So just some more visualizations. And here's another view of the Cascadia subduction zone. This is the Bob McPherson view. So here we're somewhere in southeastern Oregon looking down so north is to the right. We can see that the Gorda Plate is subducting beneath the North America Plate. And we can also see here is the San Andreas Fault that comes up to the Mendocino Triple Junction, where it also meets the subduction zone and the Mendocino Fault, which is also a strike slip fault. So these are two strike slip fault systems, which means they move side by side. And then this is the subduction zone where one plate moves underneath another. So in 1944, 1946, so here's Tokyo, this is Japan. 1944, 1946, there were some large subduction zone earthquakes, magnitude 8.5 earthquakes, something like what we might see here. And this, so Japan is the land of earthquakes. They've been studying earthquakes for centuries. They have a long record of earthquakes. So in 1944, 1946, really inspired them to start spending millions of dollars a year on studying earthquakes. And this is some of the first evidence that we have for the earthquake cycle. So first I'd like you to note that, so here's some data. This is distance from the deformation front. So the deformation front is the front part of the subduction zone here. And so going from west to east. And this is distance in millimeters. And this yellow, I've outlined this yellow line. So this is the vertical deformation, the coseismic vertical deformation during the earthquake deformation. So this part of the subduction zone went down. So this is the wrist part of the subduction zone, and this part of the subduction zone went up. And that's the fingers part of the subduction zone. Now what I can do is I'll click. And what I've done is I've just taken this dark yellow line and I've inverted it. So that red line is the inversion of this yellow line. And now I'm going to click again, and we'll note that it matches very similarly with this other yellow line. And this other yellow line is the interseismic rate, the interseismic deformation. So what we can see from these observations is that the coseismic uplift and subsidence is exactly opposite the interseismic uplift and subsidence. So that was very interesting, and so it helps us sort of try to predict what might happen during an earthquake based on what the interseismic part deformation is doing. So we can take a look at the interseismic deformation, say, well, if it's going down, it might go up during an earthquake. If it's going up, it might go down. So in 1960 and 1964, we had the largest, magnitude 9.5, and the second largest, magnitude 9.2, subduction zone earthquakes in Chile and in Alaska. And George Plathker, he went up to Alaska. So here's the map of Alaska, and he documented regions of uplift and subsidence in Alaska and in Chile. And here's a map that represents areas that he mapped that went down in blue and areas that went up in red. So which is the finger, the red or the blue? The finger part of the subduction zone. The red is the finger. So it went up during the earthquake, it went up. And the wrist goes down, so the blue area is the wrist part of the subduction zone. So here is a modern analog, just another modern analog. Now we actually have evidence of past earthquakes along Cascadia. So Brian Atwater in 1987 published the first geological evidence of past earthquakes along the Cascadia subduction zone. And so here's the little story. Now he published these figures in 2005. And so here we can see a happy tree with green leaves growing just slightly above sea level. So it has lots of fresh water. It's a happy tree. And then we have an earthquake, and the ground surface goes down, and it puts that ground surface below high tide. So now that tree is being inundated by salt water every day, maybe twice a day. And it's not very happy, so it dies, because it doesn't like the salt water. And eventually, it gets covered, the soil gets covered by silts and muds, and then, remember, it's the risk, so in between the earthquake it goes up. So it fills in with mud, and it also goes up, and eventually the ground surface is high enough to support plant growth again. There's fresh water there again. But now the tree is dead, and eventually the top of the tree falls apart, and you can only see the stump of the tree in the mud. So here is a cross section. Now this is, let's see, this is in Oregon, I think. And you can see here is the soil, and these are the layers of mud that filled in after the earthquake. So we've documented this in sites all along the subduction zone. So here's California, Oregon, and Washington. And these white dots are locations where we've documented this evidence of co-seismic subsidence, where there's a soil that is buried by mud. So here is a photo of some trees that got barnacles growing on them. Do barnacles grow on trees? No. What's happening here? Something's not right, right? Yeah, so these trees, before the earthquake, they were up above tide, and then they subsided during the earthquake, and now they're below tide, they're inundated. You can see that the tops have fallen off as they died, and now they've got barnacles growing on them. So we call this a ghost forest. This is a ghost forest in the Wappa Bay in central Washington. Well, I went up to Alaska 2 years ago, and this is Turnagain Arm. It's a funny story about Turnagain Arm. So Drake was going in around and exploring everywhere and going in through these fjords. And he got to this arm of this fjord, and they had to turn. They said, "Oh, we got to turn again?" So they called it Turnagain Arm. So this area is in the area of Blue in Alaska that went down during the earthquake. And we can see here's a tree that before the earthquake, this tree was rooted in the soil, and it was a happy tree. Then the earthquake caused the subsidence, and now it gets inundated with salt water, and it died. And eventually it filled in with this gray mud, and it went up because it's in the risk part of the subduction zone. And now plants are starting to colonize here. And you can see in the picture, but there are some shrubs, and sometime in the next decade or so, we'll get trees growing here again. So just another nice little picture. So Brian Atwater, he's compiled this on-land record of past earthquakes. And we found that we have, if we go, so let's see, here is today, going back in time to 0, and here's BC, this is AD, and each of these, so if we start here, we have happy tree growing, then the surface goes down, it gets buried, and then the surface goes up again, we have happy plants again, it goes down. So each of these vertical drops represents an earthquake. So we have a long record now of Cascadia subduction zone earthquakes. On land, the record goes back about 6,500 years. So we have over 6,000 years of earthquake records on land. And you can download this paper from 2005. If you type into your computer, the internet, do an internet search for the orphan tsunami, you can download this for free. And it's written in a way that lay people can understand it. So it's written for you. Yes, sir?
About how many years there between the subduction and then plants trees regrowing?
In Alaska, it happened within about a decade to a decade and a half. So it recovered really quickly. Different subduction zones are different. Yes, sir?
So that tree that you showed in the Alaska picture, was that from the 63 earthquake?
64, yes.
64?
It was from the 9.2 earthquake in 1964. So you can download this for free, or you can go online and buy it if you want a hard copy. Yes, ma'am.
And when you're describing the trees going down, it looks like the immediate soil that arises not because the ground is going up, but simply because soil is filling in to that space.
Yes, because the tide brings in silts and clays, and then it deposits sediment every day, or every tidal cycle.
Eventually it is going to go back up.
Yeah, eventually it starts going back up. So,
is this orphan tsunami here? Did it affect this area, or is it from up north?
I'm going to get there momentarily.
Okay.
So I'll briefly talk about the marine record of earthquakes, and this is Now I've done coring on land, but I also do coring offshore, so this is what Jane was referring to as one of my specialties. So here's our model. Here's a cross-section of the Earth with the sea levels right here, so this is all underwater. Then we have the subduction zone earthquake at depth. It causes ground shaking, and in those seismic waves, those ground motions go through the ground, and if the conditions are right, that ground motion causes landslides, submarine landslides. Those landslides go down slope, they turn into turbidity currents, and they continue down slope and leave deposits called turbidites. Excuse me. And so maybe an earthquake might have multiple pulses of energy, so sometimes the fault will slip different amounts of time, and that might cause different numbers of landslides, and then your turbidity current might be heterogeneous like that. So here's what a turbidity current might look like, but this is in the laboratory, and just to give you an idea that this sediment is just moving through the water in a very turbulent manner. And I won't go too much into the details of the sedimentology, because we have a lot to cover in a short time, but this is all documented. Here's the Cascadia subduction zone, and each of these dots represents a sediment core that my colleague Chris Goldfinger and others, including myself, have worked on. And here, this is another USGS professional paper that you can download for free. It's a little bit more technical than Brian Atwater's paper, but you can still download it and understand it certainly to a certain amount of detail. And in this paper, they present. Now I'm not going to go into all the detail of this slide. There's lots of text. I try to avoid lots of text, especially sort of in layperson talk. But I can assure you that there are a number of different ways that you can trigger submarine landslides. And in that paper that I just showed you, we go through all these different types of triggering mechanisms. And if you want to go into the detail, you can learn more about that just by reading that. I'm not going to go into that detail in this talk today. But basically, the principle is that we try to correlate these layers, these turbidites, from one core to the next core. And we use the physical properties. So here are two cores, and the light blue data is density, and this is magnetic susceptibility. And the key way that we use to correlate these layers from core to core is by looking at the shape of these curves. And so you can see how this has two big pulses of density and a small one on top. This has two big pulses of density, and maybe you could argue that there's a small one on top. And then this one has three pulses, and you could almost say that this has three pulses. Here we have two pulses, and then here we have two pulses. And this is one of the most unique ones. It kind of looks like a molar. This is T11, and this molar tooth turbidite. See how the shape of those curves look very similar. They're not perfect. And then here, this is one of Fuca. This is T11, and here's another core in Rogue, and it looks very similar. So these correlation techniques are used by oil people who search for oil. And we wouldn't be able to drive cars if we could not do this. This technique goes back to the 1930s, and this is how we find oil in the deep sea, by using this type of a method. So I'm not going to go into more detail, but needless to say, that's how we correlate these layers, and that's the main way that we can interpret these layers as being generated by an earthquake. And so, skipping through a lot of detail, these are the different rupture patches that we have been able to interpret along the Cascadia subduction zone. So some of the earthquakes rupture the entire subduction zone. Some only rupture this part of the subduction zone. Some only rupture this part of the subduction zone. And some only rupture this part of the subduction zone. And some only rupture this part of the subduction zone. We've done some more research, and there's a little bit more detail here. But in general, this is the average time in between earthquakes for these different parts of the subduction zone. And so you can see here in Northern California, the recurrence interval, which is the average time between earthquakes, is about 200 years. And the last one happened in 1700, January 26, 1700 AD. But there is some variation to that. So it's not exactly every 200 years. Sometimes it's a little bit more, sometimes it's a little bit less.
Is the number smaller there at the bottom because it's triple junction and you have more activity?
Well, you know, that's a topic of ongoing debate about why the subduction zone behaves like this. And the main reason we think it behaves like this is that this part of the subduction zone was glaciated during the Pleistocene, and so there's a large amount of sediment that deposited here during the glacial periods. And because of that, the area of the fault, because the sediment fills out and can basically make the fault area larger, we can get larger earthquakes there, and we think that has something to do with why it takes there's a larger amount of time between them. But that's just an hypothesis. So, and there's many more hypotheses.
Is the severity less when the frequency is more?
Yes. So the magnitude of an earthquake is basically the area of the earthquake multiplied by the amount of slip on the earthquake. And if the earthquake happens more frequently, it's probable that the amount of slip is less. In fact, it has to be less. So if your plates are converging at 10 millimeters a year, and you have an earthquake every year, you would have a 10 millimeter earthquake every year. But if you had an earthquake every 10 years, you would have 100 millimeters of an earthquake, generally speaking. Yes, sir?
What's the typical intensity of these ones on a 200-year?
In the middle 8s. We think we would probably have a mid-8 earthquake.
That's pretty good.
It's pretty big. So this is a plot that shows for the southern segment. This is a frequency. So here's a histogram. So this is on the vertical axis is the frequency of earthquakes that have a certain recurrence interval. And on the horizontal axis is the time of those recurrence intervals. So the largest recurrence interval in segment D is less than 600 years. And it's been about a little bit more than 300 years, 316 years since the last subduction zone earthquake. So this is about where we are in relation to the frequency of earthquakes that have a different recurrence interval. So if you go forward 50 years, which is about the lifespan of a bridge or a building that if you were going to design something, we will have passed 85% of the recurrence intervals in the next 50 years. And so if you turn that into probabilities, you would say that there is a 35% probability that we will get a Cascadia subduction zone earthquake here sometime in the next 50 years. Now, it could be longer. See, there are some interseismic intervals that are longer. But if I were to tell you that you had a 35% chance on winning the lottery, I actually might buy a lottery ticket. I don't buy them, but I might buy a 35% chance. Okay, shaking intensity. There was an earthquake in Argentina yesterday. Did anyone feel it? No? Why don't you think you felt it? Or why did you not feel it?
Covered up by this moment.
Too far away. I'll get there. Okay. There was an earthquake here yesterday. Did you feel it?
Yes.
Why did you feel it? You were close to it. That's right. All right, cool. Usually I only have the first example. Okay. So this is a plot showing how the ground acceleration, so this is peak ground acceleration in units of g, so 1 g is 1 times gravity, versus distance from the earthquake, in kilometers. It's a log-based scale, and this just shows that for magnitude 8, 9, 7, and 6 earthquakes, how the ground shaking decreases with distance. So you all have a very good understanding of this now. You're all experts. It also depends on the bedrock, or what type of material your building's on. Excuse me. So if your building is on top of solid bedrock, here's a seismogram, and the vertical axis is shaking intensity. You can see on bedrock, it's going to shake a certain amount. But once you get to sediment, well-consolidated sediment, poorly consolidated sediment, and water-saturated sediment, the accelerations increase. So it also depends on distance, but also depends on what type of material your building is sitting upon. So there were people in Santa Rosa who felt our earthquake yesterday. Santa Rosa is a large sedimentary basin, so it amplified the ground motions. So here, so I mentioned earthquake magnitude, which is the area of slip times the slip. That gives you magnitude, plus times the rigidity of the bedrock. Well, we also use what's called the shaking intensity, and this is an example of that, the modified Mercalli intensity scale. And it's a scale from 1 to 12 of increasing intensity, and it's a qualitative measure of how strong it shakes. And so MMI 1, it was not felt. MMI 12 is extreme. Damage total, waves seen on ground surfaces, lines of sight and level distorted, objects thrown upward into the air. So this is just a measure of ground motions. I'm not here to scare you. Okay. All right. But yeah. That's funny. But this is a shake map using the MMI scale that the USGS and the state of California put together as a scenario for a magnitude 9 earthquake on the subduction zone. Now we think that we're probably going to have a smaller earthquake. It's more likely we'll have a smaller earthquake focused down here. But it's just an estimate of ground motions so that people can estimate, okay, well, how many aircraft carriers are we going to have to send off the coast to help everyone, right? Because that's what's going to happen when we get an earthquake. People are going to come help us, okay? You'll have to take care of yourself for a certain amount of time. So everyone should have a go kit and water and food. Okay. So here I prepared some maps showing, this is the scenario, the Cascadia scenario for our local area. And you can see here's Arcata and South Bay. This is the Eel River Valley. So here's Eureka, here's Arcata. And you can see that this is MMI 9. And then here's MMI 8 and MMI 7. So it's going to shake strongly even in Trinity and Mendocino counties. So this is just an estimate of how strong it's going to shake. And then we think that there might be some aftershocks on some other faults. And so this is a map that I had. I had the State of California and California Geological Survey put together a shake map scenario for the Little Salmon Fault. And this is what we might expect for an aftershock along the Little Salmon Fault. You can see that southern Eureka and Fortuna are likely to experience an MMI 8, which is pretty large ground shaking, similar to the ground shaking we get in a subduction zone earthquake, but we're closer to it. So it would be probably a magnitude 7.2, 7.3, smaller magnitude earthquake, but you're closer to it, so that gives you larger ground motions. This is just an estimate of what the ground motions would be.
What's the length of time between the original slip and the aftershock?
Anywhere, in a few days, the same day to a few days afterwards, maybe, a few weeks.
Is that table bluff with the hatched pattern in it?
This hatched pattern is actually the tsunami inundation map from the state of California, the existing one. So, yeah, this is the Eel River Valley, right there, in South Bay. So Table Bluff, there's the Table Bluff Fault in between South Bay and the Eel River Valley. Thanks.
R8, you said?
Arcata, right here, is at the boundary between 8 and 9. 9. So 9, some wooden structures are destroyed. Most masonry and frame structures destroyed with foundation. Rails are bent, like railroad rails. So
With foundations?
yesterday, this earthquake was located right about there. Magnitude 4.7 earthquake. And I have some other maps I'll show you after I'm done. Okay, let's talk about tsunamis.
I just put a foundation
So we have evidence of past tsunamis also. And what basically here, again from Atwater 2005, you can all download this and look at on your own, or order the hard copy. There's a hard copy also for $15 or $20. So when this ground surface subsides during the earthquake, if there's a tsunami that has a source of sediment, it will transport that sediment, and that sediment will deposit on top of that soil that got subsided. And so you can see these black dots represent that sand sheet. And if there are plants growing, they might get entombed in that sand sheet. And then again, you have sediment filling in, and the risk goes up. And so eventually the ground surface has plants growing on it again. And here's an example from Willapa Bay in Washington. And you can see, here's the buried marsh soil here. And these are the different layers of sediment, of sand. And here's some grass. Here's a grass tuft that was bent inland by the incoming tsunami and filled and covered by the tsunami, and then later tidal mud filled that in. And again, this map shows locations along the subduction zone where we found evidence of past tsunamis. Well, for my master's research, I found tsunamis in Hookton Slough in southern Humboldt Bay. So we have them here too. Here are 2 cores that I collected along Hookton Slough. And this is the base of what I interpret to be the tsunami deposit. Here's the soil, the buried soil. And then we have coarse sediment and some rip-up clasts. So some mud and plants that were ripped up while the tsunami was traveling across them. And then eventually we get tidal mud being deposited on the tsunami deposits after that. So we have them here, but not everywhere. The green dots are cores that people have collected, my colleagues and I have collected, that have evidence of earthquakes. The red dots are cores that we've collected that have evidence of tsunami deposits. And the orange ones are some cores that have been collected that may have tsunami deposits, but we haven't tested that hypothesis yet.
Where are the orange? Can you just point out orange because I can't see it?
These are orange,
I got it. So,
and these are the red dots here.
and you say orange. How far down do you go to collect them?
6 to 7 meters is how deep we've collected these cores. So they're not everywhere. So here's a map that I put together along with Lori Dengler back in 2003, 2004. And this was the first tsunami hazard map for Northern California. Here, this is Humboldt Bay, and this represents hazard for distant tsunamis, so tsunamis from elsewhere, local tsunamis, and then local tsunamis with the worst case scenario, like during high tide with a storm surge in the wintertime, during a flood. So it's gradational. It shows a gradational hazard where there's the higher hazard is in red, intermediate hazards in orange, and low hazards in yellow, and you're outside of the tsunami hazard in white. So this is our first effort at producing a tsunami hazard map for Humboldt Bay.
Is there a place where we can see that?
One at a time.
Sorry.
It's okay.
Is that 101, that line?
Yes, this is Highway 101, College of the Redwoods here. Yes, sir.
Is that map available anywhere?
Yes, if you contact me, I can provide you a link. We still use this at the Humboldt County Fair Earthquake Room as an educational tool to help people learn the the variation of tsunami hazard around the area. We used to use it. We published this in the Times Standard in 2004, so there's a tabloid version. Yeah.
The tsunami zone signs we see on Highway 101, are they reflecting this map or something more recent?
Initially, they reflected this map, and then
Which part? The red, the orange, or the yellow?
the orange.
The orange.
Yes, but then I'll show you the next couple of maps, and we modified them a little bit after we got the next series of maps. So, but they didn't change that much, actually. This actually turned out to be pretty good. It's a little bit washed out, but a few years, I think this came out in 2009, the state of California did some numerical modeling of waves. They deformed the seafloor, and the seafloor lifts up the water column, and that water column then has, because it's above sea level, has gravitational potential, so then it sinks back down, it has momentum, and it sinks below sea level, and then the water level oscillates, and that sends out the tsunami waves. And so they did some numerical modeling and determined that this red line is where we think that the tsunami would inundate during Cascadia subduction zone earthquakes. So you can see here's Arcata. This is Samoa Boulevard right there, and here's Highway 101. Here's Eureka and South Bay. Here's Table Bluff. So here's Table Bluff, College of the Redwoods. Here's Highway 101. Now, since this happened, the state of Oregon did some modeling that was a little bit more sophisticated. It's actually the gold standard for tsunami modeling now globally. And now the state of California has adopted their methodology, and in the next year or two we'll get version 2.0 tsunami modeling for California. So we're going to get a new map coming out in the next couple of years. But this is what came out in 2009, and then with the Redwood Coast Tsunami Work Group, we put together a series of tsunami evacuation maps. So these are based on that red line, and basically what we would do is we took the red line, and if it didn't, like let's say the tsunami inundated to the middle of a field. Now, how would you know if you're in the middle of the field, if you're on inside the line or outside the line? Who would know? So we extended it to the road. So this is a little bit more conservative than the numerical model would suggest, but it's easier to use. Here's the road. Okay? So this is an evacuation map. It's not an inundation map. And it's not the signs that are currently up are based on this map. And this can be downloaded from the Redwood Coast Tsunami Work Group. And this is the whole area-wide map. And if you go to the website, you can click on certain areas of the map and get a zoomed-in version for your area. So it's really easy for anyone to figure out where the evacuation zone is.
Which map is in Living on Shaky Ground?
This one is on Living in Shaky Ground. Yeah. Let's see. So here, again, 2003, 2009, and then 2010. So sort of like the evolution of tsunamis. So basically, drop, cover, and hold on during the earthquakes. Go to high ground and stay there, because these tsunamis might last, 24 hours. So wait for the helicopter to come say it's all clear. No, they could last as long as 24 hours. Okay, now I'm going to quickly tell you about sea level rise and how the tectonics contribute to sea level. So we have had glacial and interglacial cycles, and during the glacial cycles, all the ice, there's lots of glaciers, so there's lots of water up in the glaciers, and sea level's lower. And then when those glaciers melt during an interglacial, all the water from the glaciers, it melts and fills up the oceans, and sea level rises. So right now we're in an interglacial cycle, and the sea level is high. This is just showing you going from today back 140,000 years. Here sea level's high. The last glacial maximum was about 20,000 years ago. And then we had little glacial and interglacial cycles. And the last large interglacial period was about 120,000 years ago. Excuse me. So that's the background. People with the advent of the anthropogenic forcing of climate change, we've had accelerated sea level rise because of warming of the climate, and increased melting of the glaciers, thermal expansion of the oceans, all of that. And so now we're trying to forecast into the future what sea level rise will be. And these are some two different scenarios from the International Panel on Climate Change. This is from the 5th assessment report summary for policymakers presented to the public in December of 2013. And so this is an estimate. The RCP 8.5 is the estimate of what sea level will rise if we don't change how we generate energy and emit carbon, greenhouse gases. And this is another scenario. The blue is a scenario if we take certain actions. So we're not going to talk about this, but this is what people use to sort of predict what the sea level rise will be in the future, so that you can plan. Let's say you're going to plan to restore some marshes somewhere. You need to know what the sea level is going to be in 50 years, so that you can plan the topography of your marsh correctly. So remember, we have the finger wrist part of the model of the subduction zone. So in between the earthquakes, the fingers are going down and the wrist is going up. So here we're in the subduction zone, and that's going to affect what sea level is. So if the ground is going up and the sea level is going up at the same rate, you won't have any sea level rise. Okay? But if the ground is going down and sea level is rising, you're going to have more sea level rise. All right? So we propose to, so we formed the Humboldt Bay Vertical Reference System Working Group, HumBayVert, and we have a website, hbv.cascadiageo.org, and we formed a collaboration with some partners, U.S. Fish and Wildlife Service, Northern Hydrology and Engineering, Pacific Watershed Associates, Humboldt State University, University of Oregon, and Cascadia Geosciences, my nonprofit, to try to study this by using GPS data, by using tide gauge data, and long-term benchmark surveys from the highways. So we utilize eustatic sea level rise, so that's the glacial interglacial cycle, and maybe anthropogenic forcing of sea level rise, tide gauges, and leveling the GPS data to try to figure out what's going on around here. So if you look at, I'm not even looking at my notes. So if you look at the observations at 2 NOAA tide gauges, so here's Crescent City, and here's the North Spit. So Crescent City, sea level is falling at 0.65 millimeters a year. And the North Spit, sea level is rising at 4.73 millimeters a year. So if we assume a eustatic sea level rise of 2.3 millimeters a year, Crescent City is going up at 3 millimeters a year. So it's on the finger of the wrist part of the subduction zone. It's on the wrist. And at the North Spit is sinking about 2.5 millimeters a year. So the North Spit is on the finger part of the subduction zone. So this was the existing data. So here's another plot showing the existing data all along the subduction zone. These are NOAA tide gauges, and if we just zoom in here to Northern California again, Crescent City, sea level is going down, and North Spit is going up more than the eustatic sea level rise. In fact, at the North Spit, it's going up, the sea level is rising faster than anywhere in the West Coast. The North Spit. We have the highest sea level rise on the West Coast at the North Spit. So we propose to use some tide gauge data, and we place some tide gauges, and we utilized some tide gauge data from NOAA at Crescent City, Northern Hydrology and Engineering, Jeff Anderson and Mad River Slough, Samoa and Fields Landing, Army Corps of Engineers had some tide gauges placed there recently, the North Spit from NOAA, and then we've set up a tide gauge at Hoopton Slough. So here's Hoopton Slough, Fields Landing, the North Spit, Samoa, and Mad River Slough, and then up in Crescent City. So here's our the tide gauge that we set up in the 1970s. It was located there, not too far apart from each other. Here's a photo of our tide gauge location. So the gauge is actually out underwater. This is the low tide, and then here's the data collector right up there. And so going from if we subtract the USTAC sea level rise from the tide gauge data, we get the vertical land motion. So this is the vertical land motion going from north to south. Here's Crescent City. Here's Hookton Slough. So you can see in Crescent City it's going up, and then when we get to Hookton Slough, it's going down. So Hookton Slough is going down almost 4 millimeters a year, even faster than the North Spit. Then we got our colleague to analyze benchmark elevation data from road surveys. And these dots represent differences in elevation between 1988 and 1968. And the blue colors are areas that are going down, and these warm colors are the areas that are going up. So you can see that the land level data also show that Humboldt Bay is going down. So if we combine those data sets plus GPS data, which is a third independent, these are 3 independent data sets. Here are the data for Humboldt Bay, and red is going down, so all of these sites are going down. Here's another view zoomed out. So all these green sites around Humboldt Bay are going down. Once you get into the Eel River Valley, it starts going up. And if we zoom into South Bay, we can see that Hookton Slough is going down at 3.5 millimeters a year. Here's a benchmark near Highway 101, and that's going down at over 4 millimeters a year.
So Jay,
Yeah.
Whenever we have any major earthquake offshore in our part of the world, it pops up, right?
If it's on the subduction zone, we think it would pop up.
Like that earthquake in Ferndale, that big one.
Oh, 1992?
Yeah.
The Petrolia quake.
Yeah, Petrolia.
Yeah.
We drove along the coast there, and all the real smell of rotting sea life because it had come up, and
Yeah.
the tide pools were all of a sudden exposed to the air all the time.
Yeah.
That was an example of that.
That was an example of that. Originally, we thought that earthquake may have ruptured the subduction zone. Now we think it didn't. It ruptured as a different fault, but it is a great analog of what we think might happen during a subduction zone here. So here's a map that is very detailed. It has lots of data here, and so if anyone wants to talk about this later, we can talk about it. So that's my talk. I do have some slides about the earthquake that we had yesterday, but if anyone wants to go